Hello everyone, we are from Group 7. Today we are going to present our N-Butanol plant design.
Hi, my name is Mohammad Zay and I am going to present about heat integration. This chapter includes stream data, minimum energy target and pinch temperature, grid diagram of heat exchange network, modification in process flow diagram (PFD), and percentage of utility savings. The table shows the parameters value of the streams involved. There are 7 streams with a total of 3 heaters and 4 coolers. T minimum is assumed to be 10 degrees Celsius, where the adjusted temperature of both supply and targeted temperature are calculated. In the table, the enthalpy of each stream, Q, is calculated as presented. Based on the table, it can be noted that heating requirement before integration is 4995.62 kilowatts, whereas the cooling requirement before integration is 2597.73 kilowatts. Based on the adjusted stream temperature, the flow of streams are drawn as follows. This is to help in the following calculations of minimum energy target and pinch temperature. The table shows heat cascade of the streams. The highlighted zero value of enthalpy, indicating that there is no energy flow, is the pinch temperature for cold stream, which is 90.21 degrees Celsius, whereas the pinch temperature for hot stream is 100.21 degrees Celsius, adding 10 degrees Celsius of the T minimum. On the last column of the table, it is shown at the top that the value of minimum heating requirement is 278.56 kilowatts, while at the bottom of the column, it is shown that the minimum cooling requirement is 2676.09 kilowatts. The figure presented is the grid diagram of the heat exchange network between the streams. This is done based on the specific heat flow rates of the streams, where on the left hot side, the value of specific heat flow rates for cold stream need to be bigger than hot stream, and vice versa on the opposite side. Following this, it is shown that heat is integrated between the streams as shown in the blue lines, and the minimum of heating and cooling requirements have been achieved. However, a temperature crossover between H4 stream and C3 stream occur. The problem is unavoidable and can cause the efficiency of heat exchanger to reduce. A plate heat exchanger will be considered as a countermeasure to this situation. Figure below is process flow diagram before heat integration. It can be seen that initially there are a total of 7 heaters and coolers. Next, figure below is the process flow diagram after heat integration was done. After heat integration, 4 heat exchangers are utilized and the number of heater and coolers has been reduced to 5 as shown in the figure above. To summarize the energy integration that was done, the percentage of utility savings were calculated. Below are the heating and cooling requirements value before and after integration, and computing those values, it is calculated that the percentage of energy savings for heating and cooling are 94.42% and 3.02% respectively. Although the percentage of energy savings for cooling is low, which is only 3.02%, the percentage of energy savings for heating is significantly high with a value of 94.42%. Thus, in conclusion, based on the percentage of utility savings, the implementation of heat integration can reduce the utility cost in a long term. Apart from that, the total number of heater and cooler has been reduced from 7 to 5. Lastly, 4 heat exchangers are needed in fulfilling the targets.
Okay, here are optimization of process design. And here are introduction about optimization itself. Optimization is one of the major quantitative tools in the process of decision making. The goal of optimization is to determine the optimum operating condition and physical design that could achieve best process performance of each unit operation in a plant without compromising all the constraints that are predetermined. By doing optimization, benefits such as to improve yields of valuable products or reduce yields of contaminants, reduced energy consumption, and etc. can be achieved. The optimization will then be done upon determination of achieving maximum profit of butanol, which is 1808.99 USD per IB, by minimizing the supplied reactant. Hydrogen is chosen as it has the highest price among reactants used, which is 6.35 USD per IB. The amount of total hydrogen fluoride for reaction 1 and reaction 2 need to be in minimum in order to maximize the profit of butanol. Here are the calculations. First, we need to decide the variables. Then, we need to find the objective function. Only then we can proceed to do the equality constraint and inequality constraint. And here are optimization graph of hydrogen fluoride against butanol fluoride based on the calculation that...
Hi, my name is Fatia Ali and I'm going to explain about the equipment sizing and mechanical design. There are 20 equipments in this plant, consists of bed reactor, distillation tower, expander, valves and also heat exchangers. These are the reactor specification sheets where both of it are fixed bed reactor. The first reactor is to produce N-Butadiene and isobutadiene, while for the second reactor is to produce butanol and isobutanol. These are the distillation column specification sheets, where both of it are flash column and the other one is tray column. For this equipment specification, it provided with the specific process specification with the equipment properties. These are the expander specification sheet and valves specification sheet. For both expanders, it is to decrease pressure before entering the reactor, while for the valves, it is all to adjust pressure. These are the heat exchanger specification sheets where it consists of cooler, heater and also integrated heat exchanger. For cooler, it is to provide cooling to hot stream, while for the heater, it is to provide heating to cold stream. All of the equipment specification sheets are provided with a specific operating condition and also with the equipment properties. For the next heat exchanger specification sheets, it is for cooler and also integrated heat exchanger. For both cooler of heat exchanger 420 and integrated heat exchanger, it is using floating head cross flow heat exchanger with one shell to tube passes. For the other process specification and equipments are given as detailed as it is. For the last heat exchanger specification sheets, it is all for integrated heat exchanger, which is all of it are using floating head cross flow heat exchanger with one shell, two tube passes. The equipment specification sheets are provided with the detailed operating condition and equipment properties. These are the first mechanical design, which is for the fixed bed reactor. It is to produce butanol and isobutanol in the hydrogenation process of butadiene and isobutadiene reacting with hydrogen. The operating data, specification data, and also heat and closure design are given as detailed as it is. In this design, the dome head type used is ellipsoidal with a material construction of stainless steel 316. The design type is horizontal, and all of the dimension, the specification, and also the design are given as detailed as it is. For the next mechanical design, it is for the distillation column, which is to separate isobutanol and N-Butanol as the overhead product. The operating data, specification data are given in the equipment specification sheets, where in this design, the dome head type used is ellipsoidal. This is the tray distillation column, where it consists of 25 numbers of plate, 13 rectifying plates and also 12 stripping plates. All of the dimension, the detailed design are given. For the last mechanical design, it is the heat exchanger, which is to provide enough cooling requirement to hot stream H2 from 100 to 73 degrees Celsius. The heat duty is 831 kilowatt. The specification data are given where the type used is floating head cross flow heat exchanger with a number of 1 shell to tube passes. The number of tube is 26 with a material construction for outer pipe is carbon steel inner, while for the inner pipe is the carbon steel. The heat transfer area is 611 feet squared and the tube pinch used is square pinch. All of the dimension, the detailed dimension, specification are given. For the mechanical design justification, for the heat exchanger, we are using the shell tube heat exchanger because of the area is more than 200 feet squared. All of the design, the specification are based on the Tubular Exchanger Manufacturers Association standards and ASME pressure vessel code. We are using 1 shell 2 tube passes to increase the tube side fluid velocity. We are using the floating head to eliminate the expansion problem between shell and tube when high temperature difference occur. It will also permit removal of the tube bundle from the shell so the outside surface of the tube can be cleaned. The usage of square pinch tube layout in this design is used for easy cleaning of tubes and baffles holes because in the heat exchanger the probability of the leaking will occur. For the reactor, the vessel contains nozzles for entering and exiting stream. We are using the manhole for internal access. We have saddles for support because it is a vertical reactor. The specification and design of the shell and heat thickness are based on the ASME boiler and pressure vessel code, which in this design we are including the corrosion allowance and also wind loading. For the distillation column, the design of the shell, the specification of the shell and heat thickness are based on the ASME boiler and pressure vessel code, which we include the corrosion allowance. We are using the skirt for support because it is the vertical distillation column. The distillation column contains additional nozzles and manhole for multiple feed entries and management of bottom liquids and its withdrawal. The function of tray is to reduce pressure drop, to increase purity of the product and increase the capacity. It will also give higher stage efficiency in terms of high equivalence to a theoretical stage and capacity in terms of reducing diameter. Moving on to the equipment costing. This is the equipment costing summary where the total bank module cost for all equipments is $1.742 million USD. For the grassroots capital, it consists of total module cost with auxiliary cost, which give $2.855 million USD. For the summary of direct and indirect costs, the direct cost consists of on-site and off-site, which costs $4.335 million USD, while for the indirect cost, it costs $2.227 million USD. The total capital investment consists of fixed capital investment plus with the working capital and startup costs. It gives a total capital investment of $11 million USD. For the level cost, the number of shifts is 4. The number of labor is 30% per shift, which gives 120% per day. The level cost in Malaysia is $702 per month, which is the same as 3,000 ringgit per month. The total operating level cost is $1 million per year. The summary for the material product and utilities cost, the total annual cost for raw material is 1.6 billion. The total annual cost for production is 4.0 billion. The utilities cost estimation consists of hot and cold utilities, bulk and also expander, which gives a total utilities of $6.3 million USD per year. The summary for plant manufacturing costs, it consists of direct production costs, utilities, miscellaneous, and indirect production costs, which gives a total manufacturing expenses of $2.1 billion per year. So the total production cost is equal to the total manufacturing expenses plus with the general expenses. So the total general expenses is 2.8 million. The total production without depreciation is $2.124 billion, which gives a total expenses with depreciation of $2.125 billion USD. The gross earning or profit is the annual sales revenue minus with the annual production cost, while the annual net earning is the after-tax rate of return times with the gross earning profit. This gives the annual gross earning profits of $1.899 billion per year USD dollar and the annual net earning of $208 billion USD per year.
Waste treatment. In the production of N-Butanol, a number of compounds other than the desired product is produced, in addition to the unreacted reactants present after the reaction has occurred. The compounds generated are isobutanol and isobutyraldehyde. The unreacted reactants are the remainders after the hydroformylation and hydrogenation reactions. These wastes could be reduced by considering several unit operations where waste minimization can be utilized. Several options can be applied to these streams as an effective means to manage waste production. The waste generated in the processes are from stream 8 and stream 19, which consists of unreacted reactants. Meanwhile, stream 26 is the primary waste produced in the form of isobutanol. Stream 8 is the top stream exiting the flash column FD401 for components separated from butyraldehyde and isobutyraldehyde. As such, the stream consists of unreacted propylene, carbon monoxide and hydrogen. Stream 19 is the top stream exiting the flash column FD402 for the components separated from isobutanol and N-Butanol. Therefore, the stream consists of unreacted butyraldehyde, isobutyraldehyde and hydrogen. Stream 26 is the top stream exiting distillation column BC401 after the separation of isobutanol from desired product N-Butanol. The table below shows the specification of each wastewater stream, including the temperature, pressure, phase, as well as the total waste produced in terms of kilogram per hour. Waste minimization is a set of processes and practices intended to reduce the amount of waste produced. Waste minimization can be achieved through a number of methods. Some of the methods are recycling, improved process technology and equipment, improved plant operations, usage of pure reactants, as well as effective management of catalyst waste. Since streams 8 and 19 constitute primarily of unreacted reactants, the option of recycling can be implemented. Recycling allows to reduce the amount of waste created as well as the amount of fresh feed required. In the proposed method of N-Butanol production, the most significant waste produced, apart from the unreacted reactants, is isobutanol, which is produced from isobutyraldehyde, which itself is a product of hydroformylation site reaction. Two options to handle this will be discussed in the effort to reduce waste production. In doing so, the financial implications will also be taken into consideration. From this, the more economically feasible and more attractive option shall be chosen as the preferred method of handling said waste. For the first method, the option to be considered is the building of a dedicated wastewater treatment facility. This would allow waste from the processes to be treated directly before being discharged. The treatment facility itself will be made up of various steps in order to make the discharge environmentally safe. The first step in this process is the equalization tank. The equalization tank serves as a flow rate buffer. The next step of the process is the pH adjustment. This will be done when the wastewater passes through a pH neutralizer system. The next step after pH correction will be the chemical treatment of wastewater. The chemical treatment is then followed up with a biological treatment. Since the treated wastewater is to be released into the environment and not to be supplied for human supply, tertiary treatment is not necessary. As such, after the secondary treatment, the treated water is separated from the sludge through a clarifier before being released into the environment. The figure below shows a simplified overview of the proposed wastewater treatment set to be built on site. The chemical treatment chosen is chemical coagulation, meanwhile the biological treatment is activated sludge treatment. Another option for the waste production is to market the waste product as a secondary product. In a similar manner to N-Butanol, isobutanol is a very marketable chemical. The uses of isobutanol are numerous. They are often used interchangeably as well. The main applications of isobutanol are as varnishes and precursors to ester, which are useful solvents such as isobutyl acetate. Isobutyl esters of phthalic, repeat, and related dicarboxylic acids are common plasticizers. Furthermore, isobutanol is also a component in some biofuels. Finally, although the production of isobutanol is less in comparison to N-butanol in our proposed plant, the financial benefits of marketing it as a product alongside N-butanol will make it a worthwhile solution, not to mention the reduction of waste it will result in. Moreover, option 1 requires more capital investment to provide a treatment facility in comparison to option 2 where investment is required only for the refining of isobutanol. Taking all these points into consideration, it is decided that option 2 will be the more ideal option for the proposed plant.
Process control. Reactor 1R401 is an isothermal reactor, thus a cooling jacket designed with the reactor.
There are three control objectives. To control the temperature inside of the reactor, the temperature inside the reactor was measured and the flow rate of the cooling water supply is manipulated. The control configuration is cascade control. The second objective is to control the pressure inside of the reactor. The measure variable is pressure inside the reactor, while the manipulated variable is outlet flow rate of the reactor. The control configuration is feedback control. For the third objective, the measured value is flow rate of inlet stream, while the manipulated variable is also the flow rate of inlet stream. The control configuration is feedback control.
Reactor 2R402 is also an isothermal reactor. The control configuration for reactor 2 is similar as the reactor 1.
The control objective and the control configuration for reactor R402 is similar as the reactor R401, but the temperature and pressure conditions for R402 is differ from R401.
For flash drum 1 FT401, there are two process parameters that need to be controlled, which are pressure and level.
To control the level of flash drum, the level of mixture in the flash drum was measured and the flow rate of exit liquid stream level was manipulated. The control configuration is feedback. Secondly, to control the pressure in the flash drum, the pressure inside the flash drum was measured and the flow rate exit vapor stream 8 was manipulated. The control configuration is feedback.
The control configuration for flash drum 2 FT402 is similar as the flash drum 1.
The control configuration of FT402 is similar as the FT401, but the difference in operating temperature. FT402 operate at 80 degrees Celsius, while FT401 operate at 30 degrees Celsius. So, the control system for FT402 need to set a desired point, which is 80 degrees Celsius.
There are 7 control configurations for distillation column DC401.
Temperature is an important parameter need to be controlled in a distillation column. To control the temperature inside this DC401, the temperature inside column was measured and the flow rate of steam into reboiler or the flow rate of cooling water into condenser was manipulated. The control configuration is feedback control. To control the pressure inside DC401, the flow rate of overhead stream that leaves the top of column was manipulated. The control configuration is feedback control. While to control the reflux drum level, the level in reflux drum was measured and the flow rate of distillate stream 26 was manipulated. The control configuration is feedback control.
The flow rate of heating utility into reboiler was manipulated to control the vapor composition of outlet stream. while flow rate of bottom flow stream 27 was manipulated to control the level in the column DC401. To control the liquid composition of outlet stream from condenser, the flow rate of cooling utility into condenser was manipulated. The control configuration is feed-forward cascade control. Finally, to control the composition of distillate at desired value, the flow rate of reflux flow into the distillation column was manipulated. Heat exchangers are used to cool down or heat up a stream to a desired temperature. There are 4 coolers and 1 heater in this plant. The control configuration for all the heat exchanger is cascade control. Valves are used to reduce a liquid stream pressure. There are 4 valves in this plant. The control configuration for all the valves is feedback control. Expanders are used to reduce a gas stream pressure. There are 2 expanders in this plant. The control configuration for both expander is feedback control.
This is the overall piping and instrumentation diagram for N-Butanol production plant.
Hi, I'm Maha. I'm going to present the process safety in our plant. General plant safety for production of N-Butanol. Handling and storage of N-Butanol. Fire and explosion hazard response. Inherent plant safety. And emergency response planning. Plant layout plays an important role in the design of the N-Butanol plant as it affects the operational sustainability of the plant throughout its life. Before progressing with the designing of a plant, a few factors had been taken into consideration to maximize and fully utilize the site. Factors that are affecting plant layout are economic considerations, safety, labor demand, operability, and future expansions. Overall plant layout for N-Butanol production plant. Heads-up analysis were carried out for all the main equipments in our plant design. For reactor 1R401, there are 2 study notes. Firstly, reactor vessel. Under this reactor vessel, there are 4 process parameters which are flow, temperature, pressure and reaction. The second study note is cooling water. Under this cooling water, there are 3 process parameters which are flow, temperature and pressure. The heads-up study for reactor 2R402 is similar as reactor 1R401. For flash drum FT401, there are 4 process parameters which are controlled. Firstly, flow. Secondly, temperature. Thirdly, pressure. Finally, level. The heads-up analysis for flash drum 2 FT402 is similar as flash drum 1 FT401. For distillation column DC401, there are 4 study notes. Firstly, inlet feed flow rate. Under this study note, there are 3 process parameters which are controlled, which are flow, temperature, and pressure. The second study note is distillate flow rate. The process parameters controlled under this study note are flow, temperature, and pressure. The third study note is bottom flow rate. The process parameters that are controlled under this study note are flow, temperature, and pressure. And the last study note for the distillation column is column vessel. Under this study note, there are 3 process parameters were controlled, which are level, temperature, and pressure. For heat exchanger, There are three process parameters which are controlled. Firstly, flow. Secondly, temperature. Finally, pressure. Finally, for expander, the only process parameter that was controlled is pressure.
After the interim presentation, we received several comments from Dr. Rafizana and Dr. Aziman for several aspects. First, there are unbalanced reactor input and output. There are problems in the reasoning of error, the calculation of input, reacted and unreacted species, and there are the wrong use of the heat of formation, and there are faulty in isotope calculation. TNP values are not critically justified. TNP stands for temperature and pressure. And there are some requirements of heat network integration. And there are some problems of the poor audible. This shows the PFD of the before heat integration. And this is the PFD after the heat integration, where heat integration is used by using heat exchange network to save more energy. Now we are going to the cash flow analysis. Here is undiscounted cash flow analysis where there are no discount rates being used. The cash flow can be seen at the right side of the table. While this is the discounted cash flow where different discount rates is used, which are 200%, 300%, and 430.3%. The cash flow for respective discount rates can be seen in the blue highlighted data. Now, we can see the differences between different discount rates in graph form. From this graph, we can see that different discount rates bring different payback period. Undiscounted brings the shortest payback period, while the highest discount brings the longest payback period. Based on the table of the right side, I equal to 200% brings the payback period of 1.53 years, while the discount rate of 430.3% brings the payback period of 10 years. This shows the distinct differences between the discount rates. The huge number of discount rates are mainly due to a high number of annual revenue from sales, yet low manufacturing costs.
Thank you. This video serves as a learning process. We are not responsible to any error, inaccuracy, mistake throughout this video.